The Great Pyramid. Could it have been built in just 9 months? It defies belief. But is it possible? Let's find out. This video presents a theory how to build the Great Pyramid in 9 months. The video has 2 parts. Part 1 lays out the theoretical and historical groundwork for the proposal. We'll explain what problems this theory aims to address. Then we'll cover past developments and ideas that form its basis. In Part 2, we'll describe the proposal and its key concepts: containers, fractal ramps, and fixed lift stations. At the end, we'll give time and crew estimates. Note, in this video, we enhance and colorize old photos and illustrations. Why another pyramid building theory? The goal is not to claim that this is how the Great Pyramid was built. Due to lack of evidence, no theory can be verified. Theories can only be plausible or not. Plausible theories rely only on tools and knowledge of Old Kingdom Egypt. The actual goal of this theory is to set a new minimum time frame for plausible theories. By new minimum time frame, we mean the following. A common claim is that a block needs to be moved and raised every few minutes to fit the pyramid's construction within Khufu's reign, and that this is not feasible. By the way, over the years, the blocks per minute calculations have mutated into endless variations. We'll show that, at the shortest theoretical extreme, it's possible to raise the pyramid blocks in about 9 months. Even if the proposed method was not actually used, it still sets the shortest possible time frame for a plausible theory. This, in turn, opens up plenty of room for other plausible theories to fit Khufu's reign. The real world places constraints on theories. An example is sighting. As the pyramid rises, the architect should be able to sight down the edges to verify the shape. Otherwise, the pyramid can develop a twist, a skew, or the sides may fail to meet at the top. Simply checking if the top platform is square is insufficient, as it doesn't prevent such distortions. The sighting constraint eliminates most outside spiral ramp models, as they'd block the view. One constraint has gone mostly unnoticed: the rubble. Let's first discuss its amount and shape so we can understand the implications for any proposed method. Many people think that stone pyramids are made of evenly cut, uniform blocks. This is the case only for the outermost blocks and the interior chambers. The bulk of stone pyramids are non-uniform block joined with mortar. In the Meidum Pyramid, you can see the difference, one behind the other. In the Great Pyramid, we can see about 10 meters into the masonry in the northeast notch. Under the surface, the rough-hewn blocks are no longer uniform, though they're still squarish. But deeper in the cave, it's complete, irregular rubble. Perhaps the Great Pyramid has an internal, cost-saving pattern of walls, made of squarish blocks, separating pockets filled with low-grade rubble. If we can estimate the spacing of such pockets, we could compute how much of the pyramid is complete rubble. There's a way to do this: the Al-Mamun's tunnel, today used as the entrance. Few people inside it ever look up to not bang their heads. But the ceiling is interesting, since it's the least altered part. It seems to have an alternating pattern of rubble and squarish blocks. Let's walk down the tunnel, looking straight up. If the pyramid contains pockets of pure rubble, they could be on the order of 15 cubits wide, with a framework of squarish blocks about 7 cubits in between. If so, about a quarter of the Great Pyramid is pure rubble, never even touched by a chisel, other than maybe for a rough split. To deduce the rest of the chart, we need to look at size distribution. Here's a size distribution graph for construction stone. The x-axis is the size of a block. A quote-unquote full-size pyramid block is on the left. Smaller sizes are to the right. The y-axis is the percentage of blocks of a given size. This boundary separates small blocks which can be lifted by hand, to the right, from others. We only deal with the bulk of the pyramid here, not exceptions, like some very large blocks in the bottom courses, etc. As mentioned, the common misconception is that the pyramids are made of nicely cut, uniform blocks. This chart illustrates this misconception, with nearly 100% of the pyramid made of such blocks. On the other hand, when people hear rubble, they often imagine the remains of a thoroughly demolished masonry building, with the bulk being small chunks that can be lifted, with few large pieces, and very few very large pieces. This chart shows the size distribution of such stereotypical rubble. As we'll see, the majority of the pyramid is neither. In the notch photo, we can gauge the percentage of volume occupied by full-size blocks. It's subjective, but it's maybe 40%. This chart shows the actual size distribution of the majority of the pyramid. What predominates are sizable fractions of a full block, 2/3, 1/2, down to about 1/6. Smaller fractions, including chunks that can be lifted by hand, exist, but they're very rare. And here's a complete pie chart by volume. The majority are block fractions, squarish, but not full size. To sum up this analysis, 83% of the pyramid are smaller chunks and pure rubble. But what does this have to do with construction theories? It casts doubt on many. You might ask, but don't smaller rubble chunks reduce the labor needed? In one phase they do. In another phase they do the opposite. Let's explain. In our context, the labor involving stone can be divided into 5 phases: amassing the material, transport on land or water, elevating to the needed height, transport on the platform, and setting in place. Using rubble saves time and labor in the first phase, particularly raw, uncut rubble. Most people call the first phase quarrying, but in the case of raw rubble, it's actually collecting or gathering. Even today, some old Egyptian quarries have rubble that can be collected. Collecting was done in parallel to actual quarrying, that is, extracting by force. Let's consider other phases. Assuming sled transport on a level surface, one full-sized block versus the same weight in rubble makes no difference. Both take the same effort. You just need to tie down the rubble more densely. The rubble doesn't affect transport on a level surface. When setting material in place, the rubble generally saves labor and time, as blocks don't have to be properly aligned, though rubble needs more mortar. Overall, the use of rubble benefits the builders here. The rubble problem arises when bringing the material to a higher elevation. Each rubble chunk is still too heavy to lift by hand, so we need some form of mechanical handling. You could handle each chunk individually, but this is very inefficient. The handling labor, time, and space taken up would multiply by a factor equal to the number of chunks that fit in a full-size block. The rubble must have been handled as a contained bundle along full-sized blocks. The most optimal solution would handle both equally well, and a rubble load wouldn't be bigger than a full-size block. There are 4 major ways to bring the material up the pyramid: lifting, levering, rocking, and pulling. Let's see how the rubble problem affects each one. Lifting, a common interpretation of Herodotus, proposes crane-like devices to raise stones from level to level. For many variants of this method, rubble poses a problem, especially irregular chunks. Here's why. Cranes rely on lever mechanics, with specific length and weight ratios. All serious lifting proposals work with specific numbers. Some proposals have tight tolerances between the load, the pyramid, and the machine. Since each load has to be lifted from level to level, and each machine needs operating space, this imposes limits on how densely the machines can cover the pyramid. With tight tolerances, you can't change the load dimensions arbitrarily, but this happens if you pack the rubble in a bundle. If you hoist the rubble in a net, the stones shift around, The net stretches and bends horizontally and vertically. If you place the rubble on a sled, a pallet, or in a crate, the required strong base adds a few inches to the height. This affects the lever lengths and, in turn, the machine density on the pyramid. To sum it up, lifting can handle rubble loads, but many proposed methods need to recalculate motion ranges and the resulting machine density. Let's see how rubble affects levering methods. Note that we here mean direct levering from level to level, not levers used in other mechanical methods. Rubble chunks smaller than a half a block, if handled individually, cannot be levered at all, as shown. If you bundle the rubble in a net, it would stretch and bend all over the place, plus the ropes would tear against the pyramid stones. If you pack the rubble in a crate, the stones in the multi-ton load would shift weight, tumble, and press against all sides, requiring an unrealistic crate reinforced all around. The rubble problem eliminates levering. What about rocking methods? Rocking means elevating the block by tilting it from side to side and inserting wedges after each step to create a supporting structure called cribbing. This method works well with objects dozens of feet long on a level surface with ample workspace and time.
And try to stand this 19,200-pound block by himself.
In order to move it up to this point, I just rock the block back and forth, adding weight to that end, and that opens a gap on this side, and just slide a board in. Then I add the weight to that end.
This shoring box acts like a jack, slowly raising the block.
Another example is this Stonehenge lintel raising experiment.
Rob Roy and his team took a day to raise their lintel.
But the 1992 NOVA experiment showed that with a smaller, block-sized object, this method is slow and unstable, given the tight work area on the side of a pyramid.
The cribbage is getting a little precarious.
How would rubble fare with this method? If you pack the rubble in a net, it will shift weight, and the chunks will try to slip off the sides. If you pack the rubble in a crate, its thick base will raise the center of mass, making this method even more unstable. The rubble problem eliminates rocking. What about pulling? As already shown, the rubble problem does not affect proposals involving pulling, besides the need to tie up the load more securely. In conclusion, the bulk of the pyramid, mostly smaller chunks and rubble, favors pulling methods and some revised forms of lifting. We'll now cover the history of rolling stones, not the band, but an ancient construction method. Rolling big stones for construction is first mentioned in the Bible. In the book of Ezra, Tattenai, a Persian governor, who really existed, reports to King Darius on the building of the temple in Jerusalem. Tattenai says the temple is built with, literally translated, stones of rolling. Most Bible editions translate it as large stones, assuming that the stones were so big, they had to be rolled in some way. Literal translations retain the phrase, rolled stones. The next step takes us to 550 BC, to Ephesus, Greek Ionia, modern-day Turkey. A father and son architect duo, Chersiphron and Metagenes, were building the Temple of Artemis. It was one of the future wonders of the world, 70% bigger than the Parthenon. Sadly, now it's lost to time. To transport the columns from the quarry, the architects designed timber frames with pivots fitted into both ends of a column. The columns could now be pulled by rolling, like a modern turf compactor. To transport the massive architrave blocks, they devised an even more impressive method. The ends of the stone blocks were enclosed within 12-foot-tall wheel-like frames. Vitruvius doesn't specify the quarries, but he says it was 8 miles over flat ground. Another architect, Paeonius, worked on the Temple of Apollo in Miletus, now in ruins. To transport a huge stone pedestal, he connected 2 15-foot wheel-like frames with a ring of parallel 2-inch crossbars, spaced 1 foot apart, forming a cage with the block inside. A rope wrapped around the drum-like cage. Oxen pulled the machine by unraveling the rope. It worked, except Paeonius made the mistake of using just one rope, so the machine kept veering from a straight path. The Temple of Artemis is now gone. Few people today know that, in monolith transport, it rivaled, or maybe even surpassed, the granite blocks above the king's chamber. Here's why. This is the part of a Greek temple between the columns and the roof. The whole block is called entablature, the bottom part an architrave. Here it is compared to human size. The Temple of Artemis was 70 to 80% bigger than the Parthenon, depending which dimension you choose. Most of its columns had one standard span, but the spans in the center were wider. In Greek temples, the entablature was made of separate blocks, often subdivided even further. So why does it all matter? Because some translations of Vitruvius say that what Metagenes transported were entablatures, and some say architraves. The two different words make a huge difference. If what Metagenes transported were full entablatures, then, given the temple's dimensions, they weighted 100 tons for the standard span and 150 tons for the central span. Even the standard span was heavier than the heaviest granite block above the king's chamber. Here's a comparison of the monolith transport for the Temple of Artemis and the granite blocks in the Great Pyramid. Rolling heavy stones happened again in the 19th century, when an obelisk, nicknamed Cleopatra's Needle, was moved from Alexandria to London. It weighed around 200 tons. The engineers used the same round container for both its transport on land and for its subsequent sea voyage. The obelisk was mounted within rings, then enclosed within a metal cylinder. For rolling on land, 2 rings of wooden planks covered both ends of the cylinder. Ropes wrapped around the cylinder were pulled by tugs at sea until the obelisk rolled into the water. It took 1 day and worked fine. Rolling big stones is next proposed in a 1927 book as a method for raising the lintels of Stonehenge. And yes, you see it correctly. Herbert Stone wrote a book called Stones of Stonehenge. He proposed that the lintels, 4 to 9 tons each, were sandwiched between roller timbers for a rounder shape, with ropes wrapped around, then hauled up a timber-reinforced ramp. Adding roller timbers for a round shape was successfully tested in recent years, including a version with packed branches and a wicker wrap.
Keep going! Keep it going! Keep it lifting! Be moving like that. The weight of the stone inside is causing all that basketry to move.
When rolling objects, we must differentiate between pulling by the axis and parbuckling. Parbuckling is when you wrap a rope around an object, then pull to unroll the rope. The force is applied at the top, giving you an extra 2 to 1 advantage. The need to wrap the rope is cumbersome for long distances, but not a big issue for short ones. Parbuckling has been used to load barrels and tree trunks for centuries. The extra advantage lets you roll a 3 metric ton tree trunk onto a trailer. It can even turn entire ships, like the Costa Concordia after its disaster. One issue needs to be clarified. What we're discussing here are ways of rolling the stones themselves, whether mounted in a round frame or not. Ancient Egyptians knew about rolling objects. They saw it every day. Their beliefs included Khepri, the scarab god who rolls the sun over the horizon. Rolling an object is different from transport on wheels, where the load rests on some platform, separate from the wheels. Regardless, let's set the record straight on the wheel. Some sources claim that Old Kingdom Egypt didn't know the wheel.
And all this was done by people who didn't know the wheel.
This makes it sound like no one in Egypt before the Middle Kingdom could fathom a disc rotating on an axle. This is false. If by wheel we mean a disc rotating on an axle to perform some function, then it had been known in Egypt since 8000 BC. Long before wheels used for transport or the potter's wheel, there was the humble stamping wheel, used to make regular decorative patterns on pottery. Such stamping wheels have been found 60 miles northwest of Abu Simbel. They're not transport wheels, they're small, but they tell us that Egyptians could fathom a disc on an axle 5,000 years before the first pharaoh. Millstones and potter's wheels were clearly known in the Old Kingdom. That's how food and drink was made and distributed. Wheels for transport were known in the Old Kingdom. but used only for rare, specialty equipment. Here's a wheeled ladder from the 5th dynasty tomb of Kemheset in Saqqara. An 11th dynasty image shows that these ladders were also deployed as siege machines. So why didn't ancient Egypt adopt wheeled transport widely? The transportation system of a state evolves over time. It's not arbitrary nor easily changeable. It has to be economical, fit to the physical environment, be widespread and accessible, with supporting services. Transport wheels don't exist in a vacuum. They need a road system, usually built by the state and funded by taxes. They need industries and services, wagon makers with enough paying customers. The wagon makers need timber suppliers, etc. If you use animals for draft, not farming, you have to pay for their upkeep with your transport services. Ancient Egypt did not adopt wheeled transport for a painfully obvious reason. The Nile, a natural resource, that offered most of the functions mentioned above for free. Nearly everyone lived near the Nile, its delta branches or man-made canals. If you have the Nile, you don't need to build roads or pay for draft animals. The Nile takes you downriver with the current and upriver with the prevailing winds, for free. It's not that Egypt didn't know the wheel. It's that Egypt didn't need wheel transport.
Roads? Where we're going, we don't need roads.
Besides specialized devices, did any Egyptians know about wheel transport without using it? Quite likely. Here's why. The wheel for transport appeared in Mesopotamia around 3500 BC. Lebanon is very close to Mesopotamia. We don't know how soon the wheel for transport made it from Mesopotamia to Lebanon, probably within a few centuries. And Egypt had been buying timber from Lebanon since the 1st dynasty. Egyptians were frequent visitors to the then chief Lebanese port of Byblos. The local temples had gifts with pharaoh names from every dynasty between 1 and 6. In Lebanon, cedars grew inland. There were no navigable rivers like the Nile, so the timber had to be moved to the port on sleds or on wheels. Once wagons began to be used in Lebanon, Egyptian ship crews would have seen them, because in old times cargo was delivered directly to the port. During Snefru's reign, that would have been the crews of 40 Egyptian ships. Like any people returning from abroad, the sailors would describe things they've seen, including wagons. So at the very least, sailor families would have heard of wheeled transport. They just didn't care much about it, given their attachment to the Nile. Many ideas had spread from Mesopotamia to Egypt in the past. There's no reason why knowledge of wheeled transport, even without using it, would be different. In 1894, Swiss Egyptologist Edouard Naville was excavating the mortuary temple at Deir el-Bahari. He uncovered foundation deposits, where workers placed food, offerings, and models of their tools. Among the tool models, there was a curious device which has puzzled archaeologists ever since. We'll call it a quarter arc. Over 30 models of it have been found, suggesting common use. Historically, there have been 3 theories regarding their function. Theory 1. These are models of sleds. This can't be true as Egyptian sleds were flat, not round. Theory 2. The device was used to help in fitting joints and leveling faces across blocks. It sounds impractical. If the blocks already rest on planks and stone chips, why add unstable round parts in between? The joints will snag if their sides aren't flat and parallel. The tool strikes will shift the blocks around. A sturdy, flat platform would make a better base. If you need to move the blocks around to fit the joints, placing the block on rollers of equal height would be more stable. Theory 3. To raise a stone to some height. You place the stone on top of this device, rock the stone left and right, while sliding in a wooden wedge from the other side, thus jacking up the block. If you use a solid wood stack, as usually shown, with space around you, it works fine, up to a few feet. But on a pyramid, to keep the stacks as solid as shown, yet keep the pace of work, the whole surface would be covered in a forest of solid wood towers. The big problem is, to process so much imported timber into boards, Giza would need its own timber industry, aside from stone quarrying and transport. But we don't find big lumber yards, nor official titles of overseers of such yards. Plus, Moving all this lumber up the pyramid would be a labor of its own. If you use sparse, non-solid cribbing, the stack gets unstable and hard to control in the limited space.
You can see the principal problems with this levering operation. The stack of wood supporting the block, the dunnage, becomes precarious. And when you get it up about 3 feet or a meter, the whole thing becomes somewhat tricky.
The rubble issue applies too. Rubble chunks, whether in nets, on pallets, or in crates, will shift weight if tilted. In 1977, in Caltech's Engineering and Science Journal, John Bush, class of '55, was the first to suggest that 4 such quarter arcs, wrapped around the ends of a stone block, turn it into a roller, ready for parbuckling. Bush got as far as a real-life experiment in 1981. Supposedly, 7 men could roll a 2.5-ton block. No slope is given, so it just tells us that 7 men can roll a 2.5-ton block over some non-flat incline this way. No documentation on this test is online. It may be on microfiche someplace. Bush's idea is compared to Quercifron, but it's actually closer to Metagenes and, especially, to Paeonius' cage-like roller, with its round frames connected with thin crossbars. Except Bush wisely stipulates 2 ropes. In 2004, Dick Parry, a British engineer and academic, expanded on this idea in Engineering the Pyramids. By luck, Obayashi, a Japanese civil contractor, agreed to fund a real-life test of Parry's take on this method in 1996 near Tokyo. Key findings from that test: 3 men can roll a 2.5-ton block on a flat ground. 14 men can pull a 2.5-ton block up the whole 1-to-4 ramp in less than a minute. If the rope breaks, a chalk, or a wooden beam with a square cross-section, dragged behind the block, will prevent the block from rolling back. No other method of raising stones, including sleds, offers such a safety measure. By the way, kudos to Obayashi for doing this. Maybe one day they'll fund another test. With the historical groundwork behind us, we now move on to the actual proposal. The key idea is a versatile container that streamlines logistics. The load is packaged so that it can be pushed, pulled up, rotated in place, etc. This resembles modern shipping containers which can be transported in many ways. This minimizes or eliminates transition times between different specialized teams. You don't need a separate handoff operation, like shifting the load from a wood stack to the pyramid level. The quarter arcs, if made of wood, would need many carpenters to make and repair them. Since they're generally of the same size, and you need many, is there maybe a way to mass manufacture them cheaply? Yes, if you use the quarter arcs as just shape templates, and the actual arc is made from a cheaper material, like mud brick. Before we proceed, let's do 2 basic checks. Number 1. Physics modeling can tell us if, in theory, 2 mud brick arcs can carry a load of 2.5 metric tons in a cylindrical contact with solid ground. For mud brick, there are many formulations of sand, clay, palm fiber, straw, wood, watering, etc. Optimized for compression, mud brick can reach 3 to 4 megapascals. Solved for our case, the stress is under 4 megapascals. In theory, 2 mud brick arcs can carry a 2.5-ton load. Check number 2. Did ancient Egyptians make custom-shaped mud bricks? Yes, round interlocking, etc., including in Giza. So, if mud brick quarter arcs were feasible, how could mass manufacturing be done? It could be done in a shallow ditch. A mat strip, perhaps daubed with plaster for more stiffness, wraps around the bottom of the wooden template. At its ends, the mat strip may have handles for easy removal. The wooden template is placed in the ditch, its sides secured with boards and stakes, and the outside with gravel or sand. The wooden template is removed. Short stretches of rope are then laid down inside, daubed with clay or plaster, in a specific arrangement. The form can be greased to ease separation. The mud mixture fills the form. Short wooden dowels on top create indentations. The object is pulled out in its desired shape and air-dried. The 2 grooves handle 2 separate ropes per side. In his experiment, Parry wrapped 160 feet of rope around the roller, so it could be parbuckled 80 feet, as you need twice as much rope as the distance. So much rope is unnecessary if you use 2 ropes per side, in a pulling system we'll propose later. Whether a wooden or a mud brick roller, 1 rope wraps around the perimeter. It's tightened with tourniquets and locked in place. This bracing rope only holds the roller together. Parbuckling is done with a separate rope discussed later. The ropes may be retightened after a test roll. This binding is just an example. There are other ways, such as those used in ancient Mesopotamia. As their boats show, ancient Egyptians had no problem binding arcs with rope. Once assembled, mud brick rollers can be run over a puddle of hot tar or mud to get a thin layer on their contact surface. This will protect the rope from small, sharp stones and improve the weight distribution. If the mud brick roller works for just a single transport, its low cost may still be worth it. If the mud brick cracks, but the rope holds it together and the roller makes it to its target, the mud brick parts can just be smashed and thrown into the rubble, as their cost compared to wooden arcs is very low. Rollers give you a uniform transport for all supplies, not just stone blocks, which most theories focus on. Cargo other than full-size blocks would rest on crossbeams, held in place by square inserts, the whole bound with rope, and padded with stick bundles, branches, mats, etc. The crossbeams don't need to be imported timber. They could be smaller palm trunks. To ease loading, a 3-arc container can be assembled first, filled up, then completed with the top arcs. Roller transport doesn't apply to granite slabs or oversized limestone blocks. They'll be discussed later. Assembling a roller takes longer per load compared to other methods, but rollers buy you 2 things, very short ramps and switchbacks. And these 2 things buy you lots of bandwidth. To exploit this bandwidth, we need a dense ramp network, which can be called fractal. Fractals, or branching structures, occur in nature whenever some substance, like air, blood, or nutrients, need to be efficiently delivered into a volume. Transport-wise, building a pyramid is similar, transferring a mass of stone from the ground into a pyramid shape. Menkaura's pyramid is further away and not built over, so you can still see this volume transfer. Here's the front view of the proposed fractal ramp network. Here's the top view. In this video, we're after maximal possible bandwidth, so the ramps are on all sides. Let's explain this layout. The network consists of vertical zigzag pathways or columns. Each column consists of ramps in blue and work platforms in yellow. A load travels up one column until it reaches its desired level. Most pathways end at levels lower than the very top. When the pyramid construction reaches that height, these pathways are disassembled. Despite their density, the pathways don't interfere with each other, as shown in this top view. All ramps rest vertically on the pyramid courses. The triangular overlaps within one pathway will be discussed later. Here's how a load travels in the top view. All ramps have the 1:4 slope tested in real life by Parry, so that his data can be used. In this video, we'll assume that casing stones were laid separately, so ramps will be shown resting on the stepped courses. Here's a model of a ramp on a small section of the pyramid. For clarity, we show only one ramp, but the whole network consists of many interlocking ramps. Multiple rollers are shown just to verify that a roller can freely move up the ramp. Normally, there would be only one roller on a ramp at a time. For this dense ramp network to work, all lifting work is done on fixed work platforms at the end of each ramp. There's no work crew on the ramp itself, besides, from time to time, a rope handler. Thus, no space on the ramps is taken up by crews descending from the pyramid, nor their empty sleds. We'll now show one lift cycle on this single ramp. All ramps work in sync, cycling over and over. This video assumes the casing was laid separately, so ramps are shown on the uncased surface. The ramps are made of mud brick, as in Karnak, or a mix of limestone chips and clay.
We're looking at what the pyramid ramps were built out of. Put up a retaining wall of mud and clay, and This stuff as a whole, is extremely solid.
The lift cycle starts with a roller on the lower platform. A rope handler descends down the ramp with 2 pairs of ropes. Each pair, left and right, has 2 ropes. Their loose ends can be fastened together with a hook, a loop, a knot, etc. Near the roller, a second rope handler joins the first one. They work on both sides of the roller, in parallel, to speed things up. Each handler slips 1 rope under the roller and wraps it around the recessed inner groove. The groove has a raised lip so the rope won't slip off. The handlers fasten the rope ends and step back. We now have 2 parbuckling ropes looped around the roller. The bottom sections stay close to the ramp. The upper sections stretch above the ramp. The parbuckling is done by a lift rig on the upper platform. Its key part is a ratchet crosspiece with 2 notches for ropes. The ropes have repeating knots, spaced apart a dozen or so inches. Ropes with repeating knots are seen in Egyptian art, used for surveying. Parry's real-life test showed that a 2.5 metric ton load on a 1-to-4 slope needs 14 men. If we use levers with a 4-to-1 mechanical advantage, 4 men can pull the roller up. To split the force evenly, we'll have 2 men on each rope. Manual ratcheting involves pauses during the inactive phase. To minimize such pauses, we'll have 2 sets of 4 men, alternating their lift actions. There are many ways to arrange this on the platform. The men can be seated, standing, kneeling, facing each other, in a file, or any combination thereof. The levers can be horizontal, vertical, diagonal, or combinations thereof. A lever can be just a wooden plank, held at one end, its other end braced in a hole, with a notch for the rope. A more sophisticated design is possible if it includes ideas seen elsewhere in ancient Egypt, such as suspended overhead ropes on Egyptian ships, or large wooden frames. The rig design we show is an example of a more complex version, with overhead ropes, vertical levers, and a unified wooden frame. The men pull on the vertical levers with horizontal handlebars, as if rowing. The levers have notches to grasp the rope knots. The levers have some play, to make catching knots easier. As explained, 2 teams alternate their pull actions, to make lifting as continuous as possible. Returning to the lift cycle, the rig pulls the roller onto the upper platform, and the ropes are detached from the roller. As seen in the top view, there's a triangular overlap between 2 connected ramps. A wooden drawbridge covers this overlap, letting the roller onto either ramp. Part of this bridge is fixed, as the roller will fit underneath. When the bridge is raised, its support posts underneath fold inward to make room. When the bridge is lowered, these posts fit into depressions in the ramp. 1 or more bridge operators control the bridge depending on the force required. Wooden platforms separating 2 paths existed in ancient Egypt. The bottom of the Grand Gallery was covered by a wooden ramp, which separated access to the Queen's Chamber from the downward release path for the granite plugs. In old photos, you can still see the apparent thickness of that ramp. Returning to the lift cycle, the rope handler descends down the ramp to attach the next roller. Another handler comes down the ramp above to attach the roller that's just been lifted up, completing the cycle. How do we handle the very heavy granite blocks above the King's Chamber? First, we note these are 2 separate logistical problems. A huge amount of relatively low-weight limestone blocks versus a small number of very heavy blocks. The sensible thing is to use different methods. For the heavy blocks, the most efficient one is to move all granite blocks onto the site when the construction starts, and then raise them onto each new layer as the work platform rises. The arrangement is just an example. The blocks can be anywhere. Since the work is done on a stable open platform where wood cribbing can be contained, either rocking or levering will handle the job. This would be done by a dedicated work gang. Let's call it the Granite team. While waiting for the work platform to rise, the Granite team would dress the rough-hewn blocks for the King's Chamber walls. But handling granite this way requires foreknowledge. The builders had to know the internal design of the pyramid from the start, so the required granite blocks can be assembled on site. Did the builders have such foreknowledge? There's evidence for it. In the Old Kingdom, granite was not quarried per se, but likely collected or pried off the surface. It means the quarry delivered what it would find, rather than pieces with specific dimensions. If the idea for the relieving chambers had occurred very late, say at this point, the distribution of weights of the granite slabs would likely be random, as the quarry delivered whatever it found. But it's not random. Today we can estimate the slab weights based on their profiles drawn by the Edgar brothers. This graph shows the weights of all slabs, grouped by their level above the king's chamber. The average weight in each group clearly decreases with height. The workers didn't know accurate weights of the slabs, but they could roughly estimate the force required to handle each one. Ordering the slab weights in relation to height shows planning ahead. Here are all the granite slabs above the king's chamber ordered by weight. Where is the heaviest one by far? Directly above the sarcophagus. Given the 1 in 40-something odds, it can't be a coincidence. It was put there to protect the pharaoh. This means that at this stage, the builders already knew which of the 40-something slabs was the heaviest. Again, this shows planning ahead. By the way, this also implies two things. 1. The sarcophagus has not moved much from its original location. 2. This is the real chamber of Khufu, not a decoy. If this were a decoy, there would be no point in placing the heaviest slab above the sarcophagus. This act only makes sense if the builders really cared about this specific chamber. Protecting the pharaoh here refers to how Egyptians understood it, not necessarily how modern engineers see it. The builders seem to have run out of granite parts. We don't mean running out of granite in general, as a material. We mean running out of specific granite parts for the chosen specific design. Case 1. The ceiling chambers are separated by granite spacers. But at the very top chamber, the spacers are inexplicably replaced with limestone. Case 2. Many people have noticed the deficient distribution of granite in the antechamber. There's no granite facing the Grand Gallery. It's very odd, as this is the most vulnerable wall, the most likely line of attack of grave robbers. It's possible that a granite block had originally plugged this access niche, but it didn't matter. The robbers could have just dug a bit higher and break through. The granite distribution here is also asymmetrical with no rational reason. It's as if workers had used the last granite blocks they had. These issues are consistent with having a fixed set of pre-assembled granite parts on the work platform, raised from layer to layer. It makes raising large blocks far easier, but if something gets broken during the handling, you can't replace it. Granite seems to become deficient in directions away from the king's chamber. A possible cause would have been Khufu's wish, upon reaching this level, to have his chamber built first, so he can see it. Thus, the further away from it, the higher the likelihood that a granite part got damaged and is now missing. In her book on Egyptian work gangs, Macy Roth analyzes workers' marks in the Great Pyramid. She notes the work gangs are separated into north and south sides, suggesting area division on the pyramid's platform. The king's chamber is south of this division line, but the marks in its chambers are still divided into north and south, as if the chamber itself became the focal point. This may suggest that, on this level, the work gangs built the chamber first, with the rest of the masonry catching up later. An alternative explanation for this apparent granite deficiency could be that it was granite in general, as material that became unavailable. In the Old Kingdom, granite was pried off the surface, not quarried, so maybe the builders ran out of surface granite. But it can't be the case. Within a short time after the Great Pyramid, Khufu's son Djedefre started his own pyramid in Abu Rawash, possibly similar to Menkaura's. It's now destroyed. It had at least partial, if not full, granite casing. Djedefre also had his own and family statues made in granite, and Petrie found a part of his granite sarcophagus. It doesn't look like granite in general became scarce during the construction of Khufu's pyramid, but rather specific, pre-assembled granite parts. As shown before, much of the Great Pyramid is rubble, possibly arranged in pockets. But internal chambers should not rest on a foundation of rubble, as the risk of subsidence increases. If the builders had planned the chambers from the beginning, they'd likely build them on a stable inner foundation, a narrow island of sorts, shown in green, with little or no rubble. This inner island would be roughly the size of all chambers in a top-down projection. We can't verify its existence directly, but in some places we can do a spot check. The well shaft drops down from the gallery all the way into the bedrock. Indeed, through its whole length within the pyramid, it's surrounded by squared, regular masonry with no rubble. This is consistent with an inner island, and thus with the foreknowledge of the internal design. We'll now estimate the time and crew needed for this method to raise the volume of stone in the Great Pyramid. The calculation isn't straightforward, as different numbers of ramps reach different heights on the pyramid. For example, this segment is served by 5 ramps per pyramid side, with more ramps below and fewer ramps above. The total bandwidth is the sum of all segment bandwidths. The key factor is the duration of a single lift cycle. How long before one block in the transport chain is replaced by the next one? Another issue is the existence of a rock outcrop inside the pyramid. Our volume estimate of this outcrop is based on the data from Gilles Dormion's book and this geological paper. It includes all locations where the bedrock shows on the surface, such as the northeast corner. This is the minimum shape that's symmetrical around the main axis and fits the data points. The outcrop inside is most likely terraced. In our estimate, the terraced outcrop is about 7% of the pyramid. This graph shows the time needed to raise the Great Pyramid's volume of stone using the proposed system for different lift cycle durations, given a 24-hour workday. In his real-life experiment, Parry reports a lift time of under a minute for a 15-meter ramp. The network shown here uses slightly longer ramps of 20 meters. This shifts the lift time to about 1 minute 15 seconds. For skilled workers, attaching the roller shouldn't take more than 2 to 3 minutes, bringing the cycle duration to about 4 minutes. For a 4-minute lift cycle, this method can raise the volume of stone of the Great Pyramid, minus the estimated rock outcrop, in 276 days, or about 9 months. For the whole geometric pyramid, without excluding the outcrop, it's 300 days. The delivery rate of a hypothetical average block is 6 blocks per minute. That is a block every 10 seconds. Working 24 hours a day, 365 days a year, isn't realistic. It's just a simplification that lets us compare time estimates between different models, if all models make the same simplified assumption. Realistic estimates have to assume some number of work hours per day, per season, holidays per year, but these assumptions would differ, preventing direct comparison between models. It's doubtful that heavy work took place at night, as it's too dangerous. The ability to do heavy work outdoors safely at night didn't exist until the late 19th century. The first nighttime illuminated sports events took place in the late 1870s. Though some types of work, like tool maintenance, tunneling, etc., could be done 24 hours a day. The computation of the workforce isn't straightforward, as the number of active ramps changes over time. For example, once we reach this level, these ramps are no longer used. For one lift rig, the crew is 8, plus 2 rope handlers and 2 drawbridge handlers. On the top platform, we need enough men to distribute incoming blocks, taking into account that the area shrinks as the pyramid rises. We also need men to raise the granite slabs. Parry's real-life experiment shows 3 men are needed to push 2.5 metric tons on a level surface. We also need surveyors, supervisors, repair crews, guards, messengers, etc. Here's the on-pyramid workforce estimate as a function of rising height, with a peak of about 3,900 at course 84. By the way, course 84 is roughly at the topmost space above Khufu's chamber. So in this model, the work gangs were leaving their markings there at the peak of the on-pyramid activity. As mentioned, this chart is just the on-pyramid crew. It doesn't include any workers on the ground listed now. The reason, as explained before, is that the aim of this proposal is to address the biggest choke point, the on-pyramid transport. Here are the advantages of the proposed ramp system. Unlike most external ramp proposals, Fractal ramps provide a completely free view down the pyramid's diagonal edges to monitor the shape during construction. For any work outside the pyramid, like quarrying or preparing the transport, the pharaoh can throw more people or money at it, with proportional gains in output. Not so for on-pyramid transport. Due to limited space, the on-pyramid bandwidth is set by the ramp system. Once capacity is reached, more funds or more people can't increase it. Only a more efficient system can. The ramp system shown here maximizes it, possibly to the highest degree of all realistic proposals. Many ramp systems rely on a single narrow ramp. An accident or a ramp collapse will block all traffic on such ramps. In the system proposed here, the blockage on one ramp has little impact, as the work will go on uninterrupted in all other columns. Most external ramp ideas call for ramps as tall as the pyramid. This requires an enormous volume transfer, essentially a second construction project as big as the pyramid. In contrast, the ramps proposed here are only a few courses tall. Ancient Egyptians had all components we've shown here. Ropes with regular knots, wooden frames, rowing crews, quarter arcs, round and custom mud bricks, and wooden platforms. Stone monoliths rivaling, maybe even surpassing the granite slabs in the Great Pyramid, were transported with rollers in ancient times. The crew size and performance in the presented model were verified in real-life experiments. In the most extreme case of non-stop work, the volume of stone in the Great Pyramid can be raised in just 9 months. Even if it's not how the pyramid was built, it leaves plenty of room for other realistic theories. It doesn't take miracles, but planning ahead, logistics, ingenuity, a strong state religion or ideology, which a critical mass of the population believes in. But most importantly, it takes an absolute ruler who can command all resources of a nation towards one building. Maybe this is the only miracle here, as it occurred only a few times in history. There's a recent close parallel. The Ryugyong Hotel in Pyongyang, planned for the 80th birthday of North Korea's ruler, Kim Il-sung. Its pyramidal shape is an obvious reference. This hotel never hosted any guests. It stands empty with no practical function, besides pleasing the ego of the ruler. Today, it serves only as the most overpriced screen for light shows. Just like the pyramids. Some people wonder why ancient Egyptians didn't depict pyramid building in their art. Actually, it's not just the pyramids. We're not shown the construction of the big stone temples either. Curiously, there are only 3 known photos showing the main body of the Ryugyong Hotel as incomplete, all from a distance. Seems like absolute rulers don't want to show the construction of prestigious buildings. Standing in front of the Great Pyramid, it's hard to fathom why such a gargantuan effort was put to make a building which doesn't do anything practical. In some, this incredulity gives rise to theories about aliens and power plants. You may as well stand in front of the Ryugyong Hotel and ask the same question: why was it built? They both exist for the same reason. A despot had a wish.